thank you very much again for the introduction and also for everyone to come to this Zoom meeting. So today's talk is a joint work with Igor, the person who introduced me, who is also a professor now in UCLA, and with Greta Panova, who was a postdoc in UCLA and is now an associate professor in USC. So you can say that this work is a genuine product of UCLA. Okay. Okay. So let me start.
Except when we did it, we were actually far away.
Yeah, that's true. Actually, we did it during the, I think, during the onset of the pandemic. So everybody is actually communicating online. Okay. Anyway, so let me start with a story about my sister. So my sister is a big fan of Disney. And he has always been asking me if she can come to visit LA, not to actually see me, but to actually go to Disneyland. And here is a list of 6 characters that he likes from Disney. The top ones are the one from Frozen, ordered from the least liked to the most liked. The same with the bottom one, but this one is from Mickey Mouse, also ordered from the least liked to the most liked. Okay? And one day I got curious, so I asked my sister, "Hey sis, so which one do you like more? Do you like Olaf more or do you like Mickey more?" Then he said, "Okay, I think I like Olaf more." And then I keep asking, "How about Anna and Minnie? How about this? This is Elsa. How about Anna and Mickey?" And so on. And at the end of the day, after the interrogation, I managed to find out that this is the list. This is the entire list of the characters that my sister liked, from the least liked to the most liked. What I did just now was an example of sorting under partial information, which is the motivation of the talk today. Okay. Okay. So the 6 characters that we saw just now is an example of an partially ordered set. So this is a set where you put a partial order on its element.
Swee Hong, there is some problem with the picture, at least on my end. Pasha, do you have the same thing?
Yeah, me too. The same problem.
You have to maybe close PDF, and I mean, now it's okay.
Now it's okay? Okay. So can anybody see this red light now? Okay, then it seems like it's working now. Okay, let me just
not very well.
This?
Yeah, we can see that, but it looks funny.
It's a network problem.
I see.
The internet's not good enough somewhere.
Let me see if my internet is working well. Okay, I think mine is working well. Okay. So let me thanks for the reminder. So let me just continue on this poset. So a poset is just a set with partial order, and I draw it in this way. So here we have 4 elements, A, B, C, D, and A is less than B, means that there's an arrow coming from there's an arrow from A that ends up at B. So this also means that A is less than C, and B and C are not incomparable because there are no arrows between them. And furthermore, A is actually less than D, even though I don't draw the arrow, because you can get A less than D from the transitivity, that A is less than B and B is less than D. Therefore, A is less than D. Okay. So the tire list that we saw for the 6 characters just now, that is an example of a completion of a partial order, which in our talk, we call it a linear extension. So for example, for this particular poset, there are 2 linear extensions. There are 2 possible completion, which is either A is less than B is less than C is less than D, or A is less than C or less than B less than D. One of these 2. Okay. And now, suppose that you have a friend who is, say, working with Amazon. Okay. And his job is to order n integers, which is usually arbitrary, and he needs to order it from the smallest to the largest. And at every step, your friend needs to choose can choose 2 elements. Let's say any 2 elements, let's say A and B. And he will check whether A is less than B or B is less than A. Okay. And his job is to do this comparison to figure out the real ordering of these n numbers. And suppose that one day, he just needs to leave the work early. So he asks you for help, like, hey, Pasa, can I hand you this thing and please complete the ordering? So Pasa is a nice guy. So he said, yes, I will try to help you. And now the question is that how many steps will it take Pasa to complete the partial ordering? Okay. So here, let's say that Pasa is handed this 6-element posets with this ordering that's already been figured out by his friend. Now, let's say that for his first step, Pasa just choose C and D and check whether C is greater than D. And it turns out that C is less than D. Then for the second step, Pasa is checking for B and E, and it turns out that E is less than B. For the third step, Pasa is taking D and E, and he figures out that D is less than E. And at this point, I claim that Pasa is already done. This is because by the transitivity, Pasa can actually figure out that out of these 6 elements, the right ordering is the following linear extension that's given over here. So in total, it will take Pasa 3 steps to complete this job. And the question now here is that what should be the right strategy for doing this for the general poset? Not only for this 6-element poset, but for all posets. Are there any questions up to here? Is everybody? Yes, Pasa?
Wasn't I done at the previous step already?
Uh,
With different order, I guess.
for
A, C, E, B, D, F.
So for the previous step here, it's actually not done yet because you don't know who is bigger, either D, you don't know whether D or E is bigger.
No, but E points to B, which points to D.
So D.
No, E points to B.
E
B
points to
points.
B. Very good observation, Pasa. So it turns out that it only takes 2 steps, not 3 steps. Okay, so it turns out that Pasa is better than me at ordering numbers. Okay. Yes. So the question here is that whether Pasa can do the same thing for all posets, not only for this poset. Okay. And here is a strategy that's proposed by Kislistin in the 1970s and was also observed independently by Friedman and Lineal in the 80s, in the 70s to 80s. So here is a strategy. Suppose that at every step, you can always find X and Y, these 2 elements, such that out of all possible linear extensions of P, roughly half of them has X to be less than Y. And the other half is roughly X is greater than Y. Okay? Then, in that situation, no matter the outcome, whether X is less than Y or Y is less than X, you will always reduce the number of possible linear extension by roughly one half, because there's a C over here. Then, if you keep doing the same thing over and over and over again at every step, then you will realize that once you apply the same strategy for around log number of linear extension of steps up to a constant, up to a multiplicative constant, you will already be done with the job. And as it turns out, it's actually not too hard to see that log number of linear extension is also the lower bound, up to a multiplicative constant. So this strategy is actually optimal. Okay. So the only question here is that whether you can always find these 2 elements, X and Y, that satisfies this property. Okay. And 1/3, 2/3 conjecture says that the answer is yes, you can always find them. And in fact, they say that this probability, the comparison probability, will be located in between 1/3 and 2/3. This is the reason why it's called 1/3, 2/3 conjecture, because the lower bound is 1/3, the upper bound is 2/3. Yes, question?
Swee Hong, can I ask a quick question? The slide, previous slide.
Yes.
So the runtime is at most at the log many steps. Is it a probabilistic statement? Is it like with high probability, you only need that many steps, or?
A good question. So whether this bound is deterministic or not. So the answer is yes, the bound is actually deterministic. Because at every time step, because we assume that this thing is bounded between half minus C and half plus C. So no matter the outcome, is at least you will get at least like 1/2 minus C of them that's like remaining. Okay.
Okay.
Thanks for the good question. Okay, so let's go back to the 1/3, 2/3 conjecture. So this conjecture has been open for around 50 years and is widely considered to be one of the biggest problems in the ordered theory. So solving this conjecture probably will give you the field medals, but at least it will give you an interview with the Quantum magazine. Okay, it's that kind of an open problem. So here is the reason why we choose 1/3 and 2/3 as a lower and upper bound. The reason is because of this poset, a 2-chain plus 1-chain poset. And for this poset, we see that the probability that x is less than y is exactly 1/3. Because this poset has exactly 3 linear extension, you can just directly compute it. And the probability for y to be less than x is also 2/3. So this means that the bound in the 1/3 2/3 conjecture is tight, if the conjecture is true. Okay? That's why it's 1/3 and 2/3. It's chosen as a number. And here is what is known so far about the conjecture. So there has been a lot of papers working on this problem, but I think that one of the biggest breakthrough is done by Khan and Sachs in the 1980s, where they show that for all finite poset, there always you can always find an element x and y, and furthermore, the comparison probability will be between 0.273 and 0.727. So this is still a bit far from 1/3 and 2/3, but the reason why this is a big breakthrough is because before this paper, there was no bound for general posets that has a lower bound that's bounded away from 0 and upper bound that's bounded away from 1. That's why this paper is considered a big breakthrough at the time. In fact, it's still a big thing now. And the way the Khan and Sachs do this is that they think of every linear extension as a certain region in a polytop. Then they use this mixed volume inequality. So actually they use the Alexandrov-Fanshawe inequality to be exact, in a very ingenious way, and show that, okay, if you cut this polytop in a certain way, then maybe at least some of this area will have the size of 3/11. The other half will have at most 8/11. With that kind of argument, they show these constants. Okay. And this result has been improved by Brightwell and Fresner and Trotter to somewhere in between 0.276 and 0.724. And this is what is this is like the best bound that we know so far. But one interesting thing about this bound that I should point out is that this upper and lower bound is actually tight for infinite posets. So this means that the 1/3 to the conjecture is false if you go to infinite poset. It's only true if you restrict yourself to the finite case. That is what I think is one of the reasons why this conjecture is so hard, because somehow we need to find an argument that fails for infinite poset but works for finite posets. That is the tricky part. One of the tricky part. So before I proceed further, are there any questions? Don't be shy. You can just unmute and ask questions.
So is there any fast algorithm to actually find these x and y?
That's a very good question. So like what Pasa asked is that even if your runtime is like a log number of steps, you might still spend a lot of time to find the x and y. And the answer to that question is that there is actually not a concern. There's another paper by Kim and Khan in the 90s where they show that there's a way to actually deal with that choosing this element will not add actually too much of a constant by using some kind of entropy argument. Okay, any other question? And I think I saw some question in the chat. Let me just open the chat. Do you believe that the conjecture might be false? We believe the conjecture is true. Just because of a reason that I will explain soon. Or at least we actually believe that if the conjecture is false, then it will be possible to find the counterexample. Okay. Okay, so now let me continue. Oh, wait. Before I continue, let me just say this. So now we know that the conjecture is hard. So, as a mathematician, if we have a hard problem, we do our usual thing, which is that if the general case is too hard, then let's try a special case. And the special case that I want to talk about today is posets that come from Young diagrams. So here, Young diagrams are all two-dimensional. So that means that they are all just cells that I drawn on this picture over here. And they are drawn so that the first row is always at least as long as the second row. The second row is at least as long as the third row, and so on. Okay. The elements of the posets are the cells of the Young diagram. So they are just all of these green cells. And I say that two cells, x and y, x is less than y if y lies to the southeast of x. So that means that, for example, this top left cell, this is the minimal element because every other cell lies to the southeast. And these cells, all of these boundary cells, they are all the maximal elements of the poset because there's nothing to the southeast. Okay. So this is the poset that I want to deal with. And one important, even though one easy but very important observation is that the linear extensions of this poset, they are in bijection with the standard Young tableau of the diagram, where standard Young tableau is the filling of the diagram by numbers from 1 to n, so that the rows are strictly increasing, the columns are also strictly increasing. And the bijection is by, so the box number 1 will be the smallest element of your linear extension. Box number 2 is the second smallest, box number 3 is the third smallest, and so on. This is a good news because in particular, it means that the linear extensions can be counted by the hook length formulas, which I'll explain in a minute. Okay. Everything fine so far? Okay. Okay. I saw Fasa nodding, so everything is fine. Okay. So here is what is known so far about Young diagrams. This is a recent result by Olsen and Sagan, and they show that yes, for Young diagram, the 1/3, 2/3 conjecture is true. And in fact, they actually show that the element x and y can be found in one of the following ways. First, either x is a second box in the first row and y varies across the first column. Or if that fails, then you go and take x to be the second element of the first column, and now y varies across the first row. One of these will give you the element x and y with this probability between 1/3 and 2/3. Okay. So Olsen and Sagan, they proved this by modifying an argument bilineal, which is used for 1/3, 2/3 conjecture for weak to poset. And today, I will present you an alternative proof, which is actually due to Igor and Greta, where they show that the same result by using a new algebraic tool that is called Naruse hook length formula. Okay. But before we go to the general case, before we go to the hook length form, before we go to the Naruse form, let's try just to recall what is the classical form, the classical hook length formula. So classical hook length formula is used to count the number of standard Young tableaux, which in our case is also the number of linear extension. And this formula, you can do it in the following way. First, for every cell in the diagram, you count the hook length, which is the number of cells that's either below the cells or to the right of the cells, plus the cell itself. So for example, for this boundary cell, the hook length is 1 because you only count the cell itself. For the top left cell, the hook length is 7 because there's 3 cells over on the right, 3 cells below, and 1 cell in the middle, for a total of 7. Hook length formula is just equal to 12 factorial. 12 is for the number of cells here, and divided by all the hook lengths of the diagram. This number, I claim, in fact, it's not me, actually it's a lot of other smart people in the past. They say that this number will equal to the number of standard Young tableaux of this diagram. And now Naruse hook length formula did the same thing, which is counting the number of standard Young tableaux, but the formula did it for the skew diagrams. This is a diagram where you remove some of the top cells from your poset, which in this example is this 3 box over here, these 3 black cells over here. And the partial order remains the same. You don't mess with the partial order, you only remove some cells. Okay. And for the, sorry, let me get water for a second, otherwise. Okay. So for the classical hook length formula, we just get one giant product. But for the Naruse form, we actually need to sum over all the excited diagrams, which are defined like this. And here the rule is that the black boxes can move on the south-east direction. Yes, question? Oh, no, okay. Yeah, so here the rule is that the black boxes can move on the southeast direction. And your boxes cannot leave your diagram. That's why you see that all the 3 boxes still stay in the diagram. And if there's a box, let's say this left box here, that is blocking the way of the top boxes. That's why from this picture, the top box cannot move and only the box below can move. That is the rule for the that's the rule for these axis diagrams. And if you follow this rule carefully, you will realize that there are exactly. Oh, sorry. Yes. Hank, do you mind unmute? Let me just maybe unmute. Okay. And so in particular, so in total, there are 5 excited diagrams for this particular skew diagram. Okay. And Naruse hook length formula, which was credited to Naruse, but the current form that we saw is actually due to the hard work of Alejandro Molares, Igor, and Greta Panova. And if you're interested in the history, please ask either one of them. They are all actually in this Zoom meeting right now. Okay. So they show that the number of all standard Young tableaux for this skew diagram is equal to the product of the hook lengths that you saw in the hook length formulas, sum over all the excited diagrams that we saw from the previous slide, weighted by the black cells, weighted by the hook lengths of the black cells in the excited diagram. So this formula might be a bit scary. So let's look at the picture. Let's look at the example. Okay. So here are all the 5 excited diagrams. So this means that our formula is also a sum of 5 numbers. This term here is just the hook lengths that's come from the previous, from the classical hook length formula. Now, the black cells here, they have the hook length 765. So the weight here is also 765. This one has weight 752. So the weight for the second term is a 752, and so on. This is how the Naruse hook length formula is computed. And let me just say here that there are actually other formulas to count the skew diagrams. I mean, to count the standard Young tableau of skew diagram, like the Jacobi 3D identity. But the advantage of this formula over here is that for all other formulas, I mean, like if for most other formulas, if not all, they all involve negative terms. But this one, it involves only positive terms. And that makes it work very well when you do probability analysis. Okay, that is the reason why we choose to use this formula. Okay, so now that we know this formula, let's try to use this to prove the Olsen and Sagan result, to prove the 1/3, 2/3 conjecture for the Young diagrams. And here, the strategy is that X here will be fixed at the second row of the, at the first row, as the second box of the first row. Then Y will be moved across the first column. Okay. So let's just say that we start at the top. So Y is the first box here. And by definition, the probability that X is less than Y1 is 0. This is because, remember that the top left box is also the smallest element, is the minimal element of the poset. So any linear extension, the probability is always 0. The X is less than Y. Okay. But now, as you move very, very slowly, you move the box Y going down the column. This probability will go up very, very slowly, and eventually it will be equal to 1. And these jumps that we see, the increases of probabilities for every step, is what we call the jump probabilities. Is what we write as PI. Okay. And now, suppose that all of these jumps, suppose that all of these PIs, they are all less than 1/3. Then our strategy is this. You increases the value of PI until it actually until the probability exceeds 1/3. Which in our case, this is the time when this is the transition between P1 and P2. Now, because all this jump is smaller than 1/3, then when you actually exceed 1/3, you are guaranteed to always end up in this interval between 1/3 and 2/3, which in this case is this line over here. Okay. Then after this, you realize that you are done, because this is the same as saying that the probability for X to be less than YI plus 1, which is YI is when you actually transition. This choice will give you probability between 1/3 and 2/3. And this is the pair that you use to answer the conjecture. Okay, everything fine so far? Are there any questions up till here? Okay, so this means that to prove this conjecture, we only need to show that all of these jumps are less than 1/3. And let's do that for, let's say, for the first jump, the easiest one. So for the first jump, I claim that suppose to the contrary that P1 is not less than 1/3. Let's just say that P1 is between 1/3 and 2/3. Then, if you just look very carefully, by definition, that P1 is equal to the probability X is less than Y2, where X is here, Y2 is here, is drawn in this picture. So if this is true, if this is what's happening, then you just take X and Y2 to be your choice. Then you are done. You use this to answer your 1/3 2/3 conjecture. So let's assume that either P1 is less than 1/3 or P1 is greater than 2/3. Okay. In this case, now let's look at this picture again and notice that X and Y2, they are symmetric in the sense that we can exchange their role. And if we exchange their role, say that probability P1 is greater than 2/3, then after the exchanging, the P1 will be less than 1/3. That is why you can always, without law of generality, assume that P1 is less than 1/3, just by symmetry. Okay? Okay. So now we know that P1 is less than 1/3. And now I want to show that all of them, P1, P2 up to PL, are less than 1/3. And I claim that to do that, it suffices to show that these probabilities are all decreasing, that P1 is greater than P2, is greater than P3, and so on. This is because we already know that P1 is less than 1/3. So if all these numbers are decreasing, then all of them are also less than 1/3, and therefore we are done with our conjecture. We are done with our proof. Okay. Any questions so far? No, don't be shy. If you get some confusion, please just unmute and ask. Yes, Pasha?
So is it sharp for Young diagrams, this 1/3, 2/3 bound?
Pasha asked a very good question. Is this bound sharp? And I will delay answering this question until the next 5 minutes. But I will definitely don't worry, I will definitely answer this question. Thanks for the good question. Okay.
So the
yes.
first step of swapping, is that why you need either the first row or first column?
Exactly. The swapping is so that so we can, if I only take X to be the second element in the first row, I cannot derive this. But the reason why the reason why we say that either this scenario or that scenario is to allow this swapping, to allow this symmetry. Thanks for the good question, Han. Okay. Okay. If there are no other questions, let me show you how to prove this decreasing sequence. How to prove that these PIs are decreasing. Okay. And I will only show the proof for P1 and P2, that P1 is greater than P2, because the proof of other cases remain identical. Okay. So here is the definition of P1, which is the probability that Y1 is less than X is less than Y2. So that X is sandwiched between Y1 and Y2. And if you look at the definition carefully, if you meditate on it for like 10 seconds, like 10, 9. Okay, now you finish your meditation, you will realize that this probability is the event that your standard Young tableau, or that your linear extension, the first number here must be in the first row. And the second number is also in the first row. By the same meditation, P2 with the probability of the event that for your standard Young tableau, number 1 is first row, number 2 is in the first in the first column, and number 3 is in the first row. That will be the result of a meditation. And that is a good result, because if you think about it, that number, that probability can be computed by enumerating the number of the linear extension of these two skew diagrams divided by the total number of linear extensions. But because both P1 and P2 have the same denominator, they cancel. So it is enough to show that the number of the linear extension for the diagram above is way more than the number of linear extension for the diagram below. Okay, so now the question becomes counting the number of skew diagrams. So the number of linear extension of skew diagram. And that is where we use Naruse hook length formula. So by Naruse, remember that the number of linear extension is a sum over all sum over all accepted diagrams with the given weight. So the one at the top is the skew diagrams for the P1, and the one at the bottom is the accepted diagrams for P2. Now let's compare them. So here I group two diagrams together at the bottom if their top two cells are equal. If their top two cells, the top two black cells are equal to the top two black cells of the diagram above. So 7, 6 and 7, 6. In the middle is the 7, 7, 2 and 7, 2. And for the right is the 4, 2 cells and 4, 2 cells. Okay. Now let's look at the weight. The extra weight that is given by the diagram below is 5 and 3. 5 plus 3 is equal to 8. 8 is less than 10, the extra term that appears in the top. Then for the middle one, 5 again, 5 plus 3 is less than 10. And for the right one, 3 is less than 10. So in all cases, all the sum of the weight is less than the sum of the weight at the top. This shows that P2 is actually strictly less than P1, like what Pavel said. Okay. And I claim that the same calculation can be done for all PIs, not only for P1 and P2. And now we just stop for 1 second and think carefully and wrap things up together. Then you realize that, Eureka! We did it. We have proved the result of Olsen and Sagan by using Naruse. Okay. I hope everybody's happy with the proof. Is everything fine so far? Okay. So if everybody's happy, now let me go back to the question of Pasa. So Pasa is asking if this bound is tight, if P1 can be strictly greater than P2. Like in this picture, we actually see that 5 plus 3 is strictly less than 10. 3 here is much, much strictly less than 10. So this suggests that this 1/3, 2/3 upper and lower bound in our 1/3, 2/3 conjecture is probably not sharp. It's probably not sharp for Young diagrams, and that we can actually do much better. And here, yes, question? No question? Okay.
I have a question.
Yes, Giovanni?
So I'm confused about the last step. So you said that the final probability is 1 for the last element, but why is that?
So good question. Let me just go back to the slide.
Mm-hmm.
So here, actually, I'm cheating a little bit. You see that X, there are only 4 boxes over here.
Mm-hmm.
But I actually, in this last one, when the probability is equal to 1, I say that the X is less than Y5. So I just imagine there's an imaginary box over here that's defined to be always greater than X.
Okay, I see. Okay.
Thanks
and I guess then the rest of the proof works also for this Y5.
Exactly, yes.
Okay.
Thanks for the clarification. Okay. So to go back to a Pasa question, whether or not this bound is strict for Young diagrams. And I claim that no, the bound is not strict. In fact, that is what we are going to do now. So previously, remember that for the 1/3, 2/3 conjecture, we want to find the lower bound is 1/3, the upper bound is 2/3. But now, I want to improve this bound. I claim that we can improve this so that both the lower and upper bound will be matching, which means that both are very close to 1/2. So the lower bound will be something like 1/2 minus delta. The upper bound is something like 1/2 plus delta. And this delta hopefully becomes very, very small. Okay. And this is actually what is predicted by Kansaks in their breakthrough paper. And they predict that as the width of the poset grows larger and larger, where width is the larger size of anti-chains. In our case, this is the number of rows of Young diagrams. They predict that as the width grows larger and larger, this lower and upper bound will get closer and closer and closer to 1/2. Okay. This prediction is also still an open problem. The closest one have done to actually answer this problem is by the work of Komnos, where they prove this result not for some stronger assumption, which is that the number of minimal elements are growing larger and larger. So in particular, it implies that the width is also growing larger. Okay. In any case, today we will prove this thing. We will prove this convergence to 1/2 for the opposite setting. We will not prove this for growing width, but rather we'll prove it for when the width is fixed. Okay. So here is our result. So the objects will be the Young diagrams over here, where the rows are fixed. So the width is fixed. Okay. And all of each row, they are all growing at a proportional speed. Okay. Now, I claim that under this assumption, then the comparison probability over here is actually will actually converges to 1/2. And furthermore, we actually know that the convergence speed, the decay speed, is at least 1 over square root of n. Okay. That is what I claim. Any questions so far about the statement of the result? Okay.
So what is n here? Is it the total number of boxes?
Yes, n is total number of boxes. Thanks for the clarification. Okay. Okay, so now let me so what is different here? So let me now talk about what is the thing that we did differently from Olsen and Sagan that allow us to actually improve the lower and upper bound. So previously, remember that in the Olsen and Sagan, the x is the second box. It's the second box in the first row. And y is moved across the first column. But now, x will be chosen as a midpoint of the first row. And y is instead will be moving across the second column rather than across the first column. Okay, so you do the same thing. You move the y carefully, and you realize that the number also goes up to 1, but in a different way. Before, you remember that these pi's, they are all decreasing, but here you actually see that this pi will be unimodal. And the reason why we choose these pi's, why we choose these y's, is actually to get more choices for y, so that we have intuitively more space to do random walks, more space to compare this thing to random walks, so that we can use probabilistic tools. Okay, that is the intuition, and the result of the intuition is actually the following inequality. Sorry. So let me just do a bit of hand waving and say that after several asymptotic reduction, it's like 5 pages of hard calculations, but we somehow compare these Young diagrams to random walks. And after several comparison, we realized we managed to estimate when exactly the jump is. Remember, before we have this jump probabilities, we estimate when exactly the jump is. And furthermore, we actually know that when there's a jump, this probability, the difference between the comparison probability to 1/2, is given. Now, before it is only over one Young diagram, but now it's sum over a lot of skew diagrams. Okay. The good news is that when we actually know more or less what is exactly all those diagrams. These diagrams are such that the removed black part, which is I denoted by mu here, all of them are roughly 1/2 of the giant green diagram, with the fluctuation at the order of square root, which is what written at the as the bottom equation over here. This square root fluctuation is caused by our comparison to the random walk, and in fact, this reduction is they are using Hofstadter inequality, where the error term is roughly roughly of the square root order. That's why we see this square root at this equation. Okay. Yes.
Sorry, just a quick question. So, what are you summing in the right-hand side?
So the right-hand side is sum over all number of linear extension of the skew diagrams divided by the appropriate constant, which is, since you are probabilist, you know that this is divided by the partition function. Okay. Yeah, so it's the denominator can be, we know exactly how to compute that. The only problem is actually the numerator. That's the one that we don't have a good hand on it. So this is a sum of all number of linear extension of the skew diagrams divided by the number of linear extensions of the Young diagrams. Okay. Does that answer your question, Han?
I'm saying, so How does this lambda and mu and x and y are related? So
good question. So lambda is the original shape of the Young diagram.
okay.
So mu is roughly 1/2 of this original shape, and d is the number of rows, and that is fixed. So d is fixed throughout this talk.
What do you mean mu is half of lambda? Is it
so that means
in
that
volume?
this is actually the equation over here. So mu1 is equal to lambda 1/2 plus minus square root of lambda 1. Mu2 is the same thing, and so on.
I see. Okay.
That's what I mean by 1/2. Yes.
Yeah, okay.
Thanks for asking. Yeah. I think I go too fast here. Okay, sorry. Okay, so I hope there's no other question for this equation. Okay, so now we see that this is the sum of number of linear extension of skew diagrams. And that's good news for us. Because remember, we can use the Naruse hook length formula to actually estimate this number. Okay, and it turns out that actually this number is still a bit too hard to compute. So instead of computing this number directly, we actually upper bound this number by Schur polynomials. Okay, so recall that Schur polynomial is a polynomial with coefficient in z1, z2 up to zd, and d is the number of rows. This is sum over all semi-standard Young tableaux, where this is the filling of the diagrams by numbers from 1 to d, so that the rows are weakly increasing and the columns are straightly increasing. And the power of the monomials is just the number of occurrences of the 1 to d in the diagram. And this is actually a good news for us, because I know that most of you, if not all of you here, you are all experts on Schur polynomials. Which is why if I have trouble in computing the Schur polynomial, I can just call one of you and ask like, hey, can you help me with this? I'm stuck with this. And in fact, that's what I want to do in the next slide. Okay. So by the Naruse hook length formula, we have reduced this question to checking for this key lemma, which is asking for the following asymptotic estimate, the asymptotic upper bound for the Schur polynomial, where the d now is fixed, and z1, z2, and up to zd, they are all decreasing. And they are all need to be of a more or less the same magnitude. And we actually believe that this bound is tight, because under some technical condition, we can actually show that this Schur polynomial, the left-hand side, is equal to the right-hand side up to a matching upper and lower bound. Just that the constant might be different. That's why this is an asymptotic estimate, asymptotic upper bound, not exactly upper bound. Okay, for some constant that I don't write out. The catch here is that we don't actually know how to prove this thing in the full generality. We only know how to prove this for under some technical condition, even though we believe that this is true even without a technical condition. That's why I don't write it out. Which is why I want to ask for all of you, the experts here, if any of you have an idea how to do this without the technical condition, then please let me know after the talk, and we can try to collaborate, write a new paper, prove this thing, remove the technical condition. Okay. In any case,
am I missing some notation in the right-hand side?
Yes.
You're multiplying something looking like a set.
Sorry, I forgot to write here. There's a typo here. There's supposed to be minimum.
Okay.
Minimum over this number. Thanks, Han. Okay, so in any case, even though we don't know how to prove this for the full generality, we know how to prove it in the special case that we are in. So after like 35 pages of hard work, we finally managed to figure out the proof of this result, which is that this probability converges to 1/2. And that's why we say, Eureka! We make it, ladies and gentlemen. Okay. So let me, at this point, let me just ask a question that probably some of you already have in mind, which is that, Swee Hong, is this 1/square root of n type? Can we maybe decay to 0 faster than 1/square root of n? The answer is actually yes. We can do it for a special case of poset that we call the Catalan posets. So Catalan poset, this is a special case of the Young diagram where the shape of the picture is a rectangle of 2 rows. And in this special case, the standard Young tableau of this diagram, they correspond to the dig path, which is the path starting from 0 and ends at 0, and such that it never crosses the x-axis. It never goes below the x-axis. And the correspondence is by, if number 1 appears in the first row, it means that the first step is going up. If number 3 appears in the third row, in the second row, it means that the third step is going down, and so on. The reason why it's Catalan is because these numbers, this is our called dig path. This number is equal to 1 over n plus 1 to n choose n. Or maybe let me just write it down here. 1 over n plus 1 to n choose n, which is the famous Catalan number. And Igor is an expert on this. So if you want to ask what is history, please ask him. Okay. That is why this poset is named as Catalan poset. And here is the improvement that I promised you. For the Catalan poset, we can improve the lower bound from square root of n all the way up to n to the power of 1.25. Okay. And we believe that this 1.25, this exponent, is tight in the following sense. So here is the result of experiment for n less than 100. The blue curve here is the exponent of the error from the previous slide. This red line, it stands for the minus 1.25. And our result says that as n goes to infinity, as n gets very, very large, all this blue curve will go below this red line. And we believe that what is actually happening here is that there will be another line. Let's say this green line over here. The location exactly, we don't know where, but we believe that as n goes to infinity, our blue line will oscillate between the red line and the green line. So this means that most of the time, the minus 1.25 is tight. But sometimes, for some n, you can just get very, very lucky because of number theory reason. If you just go back one slide, that somehow this probability just get very, very close to 1/2. You get lucky. And that is what we think will cause some oscillation that seems to be what is happening over here. Unfortunately, we don't know how to prove this oscillation yet, but if any of you have an idea, again, let me know after the talk and we write a new paper. Okay? Okay. So any questions so far? Yeah? No?
Are you going to explain us how do you get this 1.25?
Next slide. Thanks.
Okay.
Han is he keeps predicting what I'm going to do next. Okay. So the main reason why we can do n to the power 1.25 is because Catalan posets are simple enough because it's only 2 rows, it's a rectangle. It's nice, it's beautiful enough that all the calculations can be done by hook-link formula instead of Naruse hook-link formula. So this means that we don't need to upper bound by the Schur polynomials. We actually have an explicit exact formula. And from the exact formula, we compute exactly what is kind of the optimal choice for x and y. And from there, we found that turns out that the optimal choice for x and y, for x, is not in the middle. So remember that we choose the middle of the first row for x for the general Young diagram. But for this Catalan poset, turns out that the optimal choice is to go to the left at the scale of n to the power of 3/4. So you go slightly to the left of the middle. And for the y, you need to go even further by a choice of square root of n. These are derived as basically by, if you want me to be honest, by calculus. So we just look at the formula, we try to do several things like do partial derivatives and so on. And we say that, oh yeah, this should be the right choice. So we use that right choice, we put in the calculation, and after like 2 pages of calculation, but this one is actually not as painful as the one from before, we get that n to the power of 1.25 is the optimal choice. And here I want to say that we believe that square root of n for general Young diagram is also not tight, just like how it's not tight for Catalan. I suspect that the right exponent will be given by the first eigenvalue of the Laplacian operator for the Young diagram defined, for the random walk defined by the Young diagram. Okay? So we don't know exactly how the eigenvalues can influence. I mean, intuitively we expect that to be happen, but we don't know yet the exact relationship between them. So that is hopefully the future work. Okay. In any case, in conclusion, we have shown that for Young diagrams, for two-dimensional Young diagrams, this comparison probability decays to 1/2. Okay, it decays to 1/2 as n goes to infinity, as the number of cells grows larger and larger. So here in this talk, I present all the results for Young diagrams, but for the paper, we actually prove it for Skew Young diagrams, for skew-shaped. The same idea works, just with more calculations. However, there are no reason to expect why this result only works for Young diagrams. It should also work for other families of posets, or at least other families of nice posets. So currently, we are working on using random walk estimate to actually prove the result for the k-dimensional Young diagram. The one that we see all so far is a two-dimensional, and maybe also to other families of periodic poset. And on the other side of the talk, there's also a new kind of a Naruse-Hooking formula due to actually Alejandro Morales and Chu, his co-author, that they actually have a new kind of Naruse-Hooking formula that we believe can be applied to the Young diagram for a different regime. So our regime is where the width is fixed, but maybe for the growing width, this Naruse-Hooking formula doesn't work, but maybe the formula will work. There's also something to think about. And finally, we are also just keeping our eyes on the 1/3 to the conjecture, so that we know it's very hard. But who knows? Just in case, if we get very, very, very lucky, then maybe one day we can prove it and get our interview with the Quantum magazine. Okay. So, okay, that's a question. What about the case of shifted set of forests? Would this formula have Hooke formulas? Good question by Per Alexanderson. That is a good question. So there's also something that can be done by using those new formulas, both of these things with Hooke formulas. So I would say that the intuition is that for this argument to work, to get this 1/2, what we need is actually some kind of product formulas, some kind of nice product formulas where we can split this thing in asymptotic. So even though for this Young diagram, we see it's a big sum, but as you take the asymptotic as n goes to infinity, what you will see is that a lot of them reduce to basically a product of two Hooke links. That is actually the intuitive, like the underlying reason behind why this works. So if there are all families with that formulas, then this same argument will work. Okay. Any other question?
Okay, that's my actual job. Thanks so much, Swee Hong, for the talk.